All right, so force in Newton's first and second law, Giancoli 4:1 to 4:4. We're moving on to chapter 4 of Giancoli. A force, push or pull, an object at rest needs a force to get it moving, obviously. And a moving object needs a force to change its velocity. And we can measure force magnitude by using a spring scale, among other things, right? But scales will measure force. So think about that. A force, push or pull. If you're at rest, you need a force to get moving. And if you want to accelerate or change your velocity, you also need a force to happen. So Newton's first law kind of goes along with that. It's called the law of inertia. And every object continues at its state. It could be rest or constant velocity in a straight line as long as no net force acts on it. So you'll either stay what you're doing at rest or at constant velocity unless a net force is acted upon it. All right. And in this example here, the book is being pushed along the table, but friction is pushing back. So these two forces are balanced, which means we're going to move at a constant velocity. Okay, so balanced forces is another term that we're going to have to think about. So inertial frame of reference, it's one in which this law is valid. Okay, so we're not talking about things that are rotating and things that are accelerating. So we're not talking about spinning things or things that are going faster, right, or slowing down. When we talk about inertial frame of reference, this is when we talk about the first law being valid. Okay. Again, that seems like something we won't talk about a whole lot, but that's just a point to make. So here's an example. A school bus comes to a sudden stop, and all the backpacks on the floor start to slide forward. What force causes them to do that? Well, first off, if it comes to a sudden stop, that doesn't necessarily mean that there's a force on the backpacks. There's a force on the bus, and the bus stops, but the backpacks will continue moving at their constant speed until a force acts on them. So they will slide forward until friction slows them down or until they hit somebody's feet that stop it, or one of the seats maybe on the school bus that stops it. But the force is not making them going forward. Okay, the force will stop them, whichever that is. But what makes them go forward is inertia, and inertia is not a force. Okay, inertia is just something that happens with matter. Let's go back to that. Maybe. Let's go back to that because I want to say one more thing about that. There we go. Again, not a force. Inertia is something that happens to matter. And inertia is very important to think about. It's what you continue to do, right? It's what keeps you moving. So if we go back here to the definition of the first law, continues its state of rest or uniform velocity. That's what inertia is, keeping what you're doing going. So inertia means you don't change. Once you stop that state of inertia, then that's going to be when you have your forces making it accelerate, either speed up or slow down. Okay, so mass. Mass is a measure of inertia. When we talk about inertia, mass is what we use, and the unit for mass is always going to be kilograms. Okay, don't try to use grams or milligrams in weight or in calculations. Always go to kilograms. Mass is not weight. Okay, mass is a property. Weight is a force. So mass is when we talk about the mass of an object, that's how much matter it has. Just like inertia is a property of matter. It's all inertia is our ability to keep doing what we're doing, just like mass is. So mass and inertia are kind of together, equal. Weight is the force exerted on an object by gravity, and so that will depend on where you're located, right? Like gravity on the Earth is 9.8, but if we go to the moon, it's 1/6 that. So you'll weigh much less on the moon. However, your mass will stay the same because the amount of matter will not change. Newton's second law of motion is essentially an equation. It's just a relationship between force, mass, and acceleration. So net force is equal to mass times acceleration. And this is Newton's second law, and that's what we're going to do some calculations with today, just to make sure you understand how that all relates. And we'll relate it back to our kinematics. So force is a vector because acceleration is a vector, okay? So When we talk about change in force, we can have positive or negative numbers. The unit of force is the Newton, all right? And the Newton, as you can see here, is kilograms times meters per second squared. So when we solve for force, our mass has to be in kilograms and our acceleration has to be in meters per second squared. Now there are other systems that we can use grams, and that's the dyne, and that's grams times centimeters per second squared. That's kind of, I mean, you can use that, but newtons are what we deal with all the time in physics. Then, of course, in our system, is the mass is the slug, but force is the pound. And there are conversion factors here if you ever needed to do that. Pound is a unit of force, not of mass, and therefore cannot be equated to newtons. But can be equated to newtons, but not to kilograms. So pounds and newtons go together, but kilograms and pounds do not. Okay, example 4.2, it says estimate, but I do the problem. Force to accelerate a fast car, estimate the net force needed to accelerate A, 1,000 kilogram car at 1/2 g, or B, a 200 gram apple at the same rate. Do it now. Example 4.2, force to accelerate a fast car. It says estimate, but I'm going to go through the work. The net force needed to accelerate a 1,000 kilogram car at 1/2 g and a 200 gram apple at the same rate. So Newton's second law, force equals mass times acceleration. Actually, net force or change in force is equal to mass times acceleration. So for letter A, our force is what we're solving for, or the force required. We take our mass has to be in kilograms, so I have a 1,000 kilogram car at 1/2 g. G is 9.8, so it's 1/2 times 9.8. And then we can see that force, so get the calculator out. And I got 1,000 times 1/2 times 9.8, and I get 4,900 newtons. B says we have a 200 gram apple at the same rate, so 200 grams, now we want to put that in kilograms, so move the decimal 3 to the left, times 1/2 times 9.8 equals 2 plus 0.5 times 9.8. I get 0.98 newtons. So you can see the difference in mass is huge when we talk about the net force that's required to accelerate. So accelerating the car requires a lot more force than it does to accelerate an apple. Force to stop a car, example 4.3. What average net force is required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour within a distance of 55 meters? This problem will kind of tie in Newton's second law and kinematics. Do it now. All right, example 4.3, force to stop a car. What average net force is required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour within a distance of 55 meters? Okay, so we got a car, all right, that we want to come to a stop. Okay, so we have a starting velocity of 100 kilometers per hour, and we want to finish at 0 kilometers per hour, and we want this distance to be 55 meters that we travel. And to find the force, is mass times acceleration. Well, we know the mass of the car is 1,500 kilograms. We find the acceleration, we can find the force. So with this information, we need to find acceleration. Now, first thing I want to do is take my 100 kilometers per hour and convert it to meters per second, right? So we multiply by 1,000 and we divide by 100 kilometers per hour, and we multiply by 1,000, and we divide by 3,600. And we get 27.7 meters per second. Of course, this is still 0 meters per second. second. This just gives us an acceleration in meters per second squared, which is what we need to solve for force. All right, so we have positions and all of this. We don't have time, so we have to use this equation. And we want to solve for acceleration. So our final velocity is 0. Our initial is 27.7 plus 2a, 55 minus 0 times 55. So let's do some fancy math here. I'm going to keep this though. 0, I'm going to write this out, plus 2 times 55 at 110a. Bring the 110a over. Divide by negative 110, which will give me a nice negative number, which is what I want for my acceleration. And I take 27.7 squared, divided by negative 110, and I get acceleration of negative 6.98 meters per second squared. I then take that number, put it in here. Now this is going to give me a negative answer, and we'll explain what that means. But when I get that answer, I get a huge amount of force. I'm going to keep it at 3 sig figs, I guess. But it's negative. What that means is the car's traveling in this direction. The force required to stop it is going to go in the opposite direction, or left, which in this case is going to be my negative. So my force is going to be applied this way at 10,500 newtons approximately. And that's what will slow my car down to a stop in that frame. So that's how you can use that information. So don't forget your kinematics equations, important to remember.